All right, time to start. Today we're going to be talking about numerical integration. It's a very fun subject. We're only going to see the very tip of the iceberg here. If you want to look more, you see a more in-depth look at numerical integration, I encourage you in the future to take the numerical analysis course that's offered here. And we talk a lot about numerical integration, and it's quite fun indeed. Okay, so announcements. There's another quiz after class today. So make sure you get. It'll be due. I'll make it due Wednesday night. Give you a little bit of extra time. But that's that. Due Wednesday night. Okay. And then again, remember to fill out course evals, fill out course evaluations. Okay. Because again, I'd very much like to hear what you guys felt went right, what went wrong, and ways I can improve it. Okay. Are there any questions on these announcements? All right, then let's get into it. So, integration. You guys have probably seen by now, hopefully you get the idea that integration allows us to find the area under curves, right? Especially when you know an antiderivative of the function we're integrating. In real life, though, most of the time, we don't know an antiderivative of the function we're integrating, right? The examples I've shown in class have been very specially chosen so that we can find an answer using the fundamental theorem of calculus. And in fact, in a lot of cases, you can show that a function that you're integrating actually doesn't have a simple, what's called elementary antiderivative. So for instance, if you're looking at the integral of e to the minus x squared dx, there's no function, no elementary function that you can write down that has e to the minus x squared as a derivative. You can try to find it. You're never going to, just by writing down e to some function. Oh, there's a question. Is there a difference between integration and anti-differentiation? Integration is a more general process of finding areas and also general antiderivatives, but no, not really. But anyway, if you try to find a simple antiderivative of e to the minus x squared, you're not going to find it. In Calc 2, for anyone who's taking Calc 2, we're going to find another way to write down an antiderivative of e to the minus x squared. It's not some simple thing that you can calculate in any finite amount of time. Okay. But this is a very difficult thing to try to evaluate, especially once you add bounds, -1 to 1, for instance. Okay. So for that reason, we need to know if I'm finding an integral. Integrals are really important. We're not just taking integrals of random functions. In real life, integration gets you from acceleration to velocity to position, right? So it's an important thing that we need to be able to do. Most of the time, we can't do it exactly. So today we're going to learn how to find an integral approximately using the function that we're integrating on its own, okay? So we already know how to approximate integrals, right? How do we approximate an integral? Who remembers? How do we, up until this point, how did we approximate the area under a curve? Three in the chat. Yes, Riemann sum, exactly. We found areas of rectangles underneath the curve, special rectangles, right? That had either their left edges go all the way up to the function or their right edges go up to the function. And as I mentioned before, you can actually use rectangles where any point on that top edge of the rectangle goes up to the function, the curve. Okay, so we'll look at an example of that. We're not going to harp too long on Riemann sums today because we've seen them before, but that's one way that you can approximate an integral is with Riemann sums. Okay, so let's look at an example of doing this. We want to find the integral from -1 to 1 of e to the minus x squared over 2 with respect to x. As I said before, this integral, I mean, you can take my word for it, or if you want, you can try to find an antiderivative of e to the minus x squared over 2. You can try to find an antiderivative. I promise you'll never find one that's a nice, simple, in a nice, simple form. Okay. So we want to evaluate this, though. This is an important integral that comes up in if anyone's taken statistics. This integral, when you look at a z-table, if anyone, again, has taken statistics, or if you're going to, a z-table is just, all it is integrals of this thing between some fixed number and some other fixed number. The z-table tells you the area underneath this curve, essentially, multiplied by a constant. Okay, so this is a really important thing that we need to be able to integrate. Okay. And like I said, it's impossible to find a simple antiderivative. Calc 2, again, you're going to find a non-simple antiderivative. But let's try approximating it because we can't find it exactly. So to approximate it, we're going to use a left Riemann sum with 4 rectangles. Okay. So let's draw out what's happening here. I'm doing a left Riemann sum with 4 rectangles. -1 to 1. Well, this curve between -1 and 1 looks like this. How do I know that? Well, I've seen this curve a lot. Or if you don't know, you can plot it in Desmos. You can do curve sketching that we learned this semester. There's a bunch of different ways that you can find out what this curve looks like. Okay. But we're trying to find this area. Okay. -1 to 1 x y. We're using n equals 4 rectangles going up to the left edge, right? So I'm going to have a bunch of intermediate points down here. What should the step size between all of my points be? I'm trying to fit 4 rectangles into this interval of length 2, right? The interval -1 to 1. So what should my step size be? Yeah, exactly. And the way we get that, we do 1 minus -1, which is 2. Divide that by, I'm trying to fit 4 rectangles into this interval of length 2. So I'm going to get 2 over 4, which is 1/2. Very good. So the step size is 1/2. So I'll get a point here, one here at 0, and one here at 1/2. So I'm using these rectangles then to approximate this area. And the whole point of today is, well, these rectangles don't look like a very good approximation. Can we find other shapes to put under this curve that maybe will give me a better approximation? That's kind of the whole point of today. And in general, numerical integration is all about finding what's the best shape to use to approximate these areas. Okay. But we can see these rectangles here. So then I need to find out the area under the curve. Well, that's just going to be approximately the area of these 4 rectangles added together, right? So what's the area of the first rectangle? Well, it has a base of 1/2. The length of the base of the rectangle is 1/2. And what's the height of that first rectangle on the left? One half times what? Exactly. And f for us is this e to the minus x squared over 2. Exactly right. So f of minus 1 is just e to the minus 1 over 2. Yeah, gotcha. Okay, any questions on where that e to the minus 1 over 2 came from? Okay. What about the second rectangle? Well, it has, again, a base of 1/2. And then I'm going to multiply by, well, what's the height of that rectangle? Yeah. E to the minus. So I'm going to get e to the, I'm going to square minus 1/2. So I'm going to get e to the minus 1/4 over 2. So that gives me e to the minus 1 over 8. Okay. Questions on that?
Could you just re-explain that for me?
Yeah. So again, all this is f of minus 1/2, which is going to be e to the minus, well, when I take minus 1/2, there's x squared, and then divide by 2. Minus 1/2 squared is 1/4, and then I need to divide that by 2. So I'll get minus 1/8 in the exponent.
Thank you.
Mm-hmm. All right. So the third rectangle. By the way, I'm taking my time writing this out. We know we've done this before with summation notation. So if you want to just jump straight to the summation, that's also fine. But I'm working this out in more detail. So the next rectangle has again, a width of 1/2, just like they all do. And what's its height? Careful. So we're going to have e to the, we're evaluating here at 0, right? So we're going to get e to the 0, which is just 1. And then last one, plus 1/2 times, well, this rectangle has the same height as this rectangle. If I were better at drawing, that would be more clear. But its height is e to the minus 1/8, right? Okay. So then if I write that out, I'm gonna, all of these terms have a 1/2 in common. So I'm gonna say this is equal to 1/2 times e to the minus 1/2 plus 2 times e to the minus 1/8 plus 1. And when I type that into a calculator, 0.5 times exp minus 1/2 plus 2 times exp minus 1/8 plus 1. Does it do it? I thought it would. E to that. Yes, it does. Okay. So when I type it into a calculator, we get about 1.686. So are there any questions about how we found this approximation here? So this is something we've done before, and this is really where the definition of the integral comes from, is first approximate the area under a curve with a bunch of rectangles, and then you let the number of rectangles go off to infinity, right? So that's really where the definition of the definite integral comes from. So that's the main idea behind numerical integration. That's all it is replace the area of some curvy object that you're trying to find, replace the area with the area of objects that you know the area of. Rectangles, we're going to use trapezoids, and we're also going to use parabolas, which we can, through the fundamental theorem of calculus, find the area under a parabola pretty easily, and then use that to get a better approximation for the area. Okay. Oh my God, chat. Okay. So when we use rectangles, you can just call that a Riemann sum like we did before. When we use trapezoids, that's going to be called the trapezoid rule. Surprise, surprise. And sadly, when we use parabolas, it's not called the parabola rule. It's called Simpson's rule, because a guy named Simpson was the one who discovered that you could integrate in this way. So we're not going to focus too much more on using rectangles because we've done that before. It will be on the quiz, but again, we've done that a lot before, so we're going to focus more on the trapezoid rule and Simpson's rule today. So let's illustrate the trapezoid rule with an example. So we're going to try to find the area under the curve given by y equals sine of pi x squared between x equals -1 and x equals +1 using n equals 5 trapezoids. Okay. So what does this function look like? Well, I don't know. Let's go plot it in Desmos. Let's look at sine functions, sine of pi times x squared. There we go. And we're specifically interested in integrating this between x equals plus or minus 1. Nope, Chase, come on. You're better than this, Chase. There we go. So we're integrating under this M-looking thing, right? And that's what we want to find the area of. So to do that, we're going to use 5 trapezoids. So -1 to +1, and we just saw that this looks like something like that. Let me move my 1. There we go, perfect. All right, so what does it mean to use trapezoids in this case? Well, trapezoids in general, let me move over here. Trapezoids in general, for general functions, are going to have, just like before, we're going to find some xi's and some xi plus 1 points. We're going to find those just like we did before. We're going to have the same fixed width of our trapezoids, but now instead of only going up to the function on my left edge, or only going up to the function on the right edge with a rectangle, now on the left edge we go up to the function, and on the right edge we go up to the function. Okay. And then we are interested in finding the area of this trapezoid. Okay. So in particular, it could be the case that your trapezoid happens to be a rectangle, right? It could be the case that if we come over here, well, right there and right there, the function's roughly at the same height. We're going to have what looks like a rectangle. Or we could get what looks like a triangle, right? We could have something that looks like that, and that's fine. Okay? So trapezoid rule, really, we're using either trapezoids, triangles, or rectangles to approximate the area under the curve. When we actually write out the rule, we don't need to make any special distinction. It's going to fall out just by looking at how do we calculate these areas. Okay. Come on, go back. There we go. All right, so let's look at finding the approximate area under this curve using trapezoids. Okay, so first of all, I'm going to have, again, these trapezoids are all going to have the same fixed width. Okay, so what should the width be if I want to fit 5 trapezoids into this interval of length 2? Two-fifths, exactly right. The length of the interval is 2, 1 minus 1. I'm fitting 5 trapezoids into this interval. If the word trapezoid freaks you out, I mean, what would we do for rectangles? We would take 2 and we divide it by the 5 rectangles we're trying to fit in. Same thing here. All these trapezoids have the same width. Okay, so delta x is 2/5, which is 0.4. So then I'm going to have my xi, just like before, is x0 plus I times delta x. So for us, that's going to be -1 plus I times 0.4. Or times 2/5, whatever you want to write down. Okay. But whatever we write down, here's what the drawing looks like. We start here. So my first trapezoid is actually going to be a triangle. Its left edge is actually just the point where the curve meets the x-axis. Okay, then I come over 0.4 to minus 0.6. So 0.4 is about there, minus 0.6. And I come up to the curve there. Okay. Then I come over another 0.4 to minus 0.2. And I come up to the curve there. So I'm going to get something that looks like that. And I come over another 0.4 to positive 0.2. And this middle trapezoid looks more like a rectangle because of the symmetry. I come over another 0.4 to positive 0.6. And I get a trapezoid that looks like that. And then lastly, I'm going to get another triangle for my trapezoid, right? So we want to find the sum of these areas of these trapezoids. And that will give us an approximation of the area under y equals sine of pi x squared. Okay. Yeah, so we're definitely going to get an overestimation for that rectangle in the middle, right? For that, well, really that trapezoid in the middle. But we're also going to get over or underestimations with that trapezoid and with that trapezoid. So hopefully the overestimations and underestimations will cancel out in some sense, but there's nothing we can do as with the trapezoid rule to try to adjust for that overestimation or underestimation. We're just using another way to approximate this integral. Okay. So the only other thing we need to know is, well, what is the area of a trapezoid? Does anyone know the area of a trapezoid off the top of their head? If I have a trapezoid, a general trapezoid for us is going to have a width of delta x, a height on the left of f of xi, and the height on the right of f of xi plus 1. Does anyone know the area of that trapezoid? Yeah, if you don't know, you could just use Google. There's a couple of different ways you could find it if you don't know. You could chop this into a rectangle and a triangle, right? The area of the rectangle is delta x times f of xi. And then the area of this triangle in SU blue is plus, well, it has a width of delta x as well, and it has a height of f of xi plus 1 minus f of xi. And then you need to, with the height of or with the area of a triangle, you divide by 2, right? Base times width divided by 2. So when you go through and you do that, you're going to find that this is equal to, well, you can factor out a delta x times, well, this is f of xi minus f of xi over 2 gives me plus f of xi over 2. So I got plus f of xi over 2, and then plus f of xi plus 1 over 2. If you go through the algebra there. And so we could write this as one fraction, delta x times f of xi, the height on the left, plus the height on the right, divided by 2. Okay, this is the area of a general trapezoid that we'll be looking at. Okay. And this works even if f of xi or f of xi plus 1, even if one of those is 0 and we're just looking at a triangle, right? If f of xi is 0, well, then we'll just get the width of a triangle times the height of the triangle divided by 2, right? That's the area of a triangle. So there's no need for us to make any special distinction. Oh, sorry, this should be an xi plus 1. My bad. There's no need for us to make any special distinction when we're writing out our work with the trapezoid rule as far as, well, is this really a trapezoid or is it really a triangle? There's no need for us to worry about that because it's taken care of in this formula. Okay. So let me cut this out really quick. Delete, and let me copy this. Copy, paste. Excellent. So this is what we're looking at here, right? So I want to find the red area. So I can say A is my approximation of the area. Well, what's the area of the first trapezoid, or in other words, the triangle on the far left? Well, all of these have a width of what? .4, exactly. So my width there is 0.4 times, well, I'm just going to plug into this formula. F on the left is 0 pretty clearly, right? So I'm going to get 0 plus, I want f of minus 0.6, where f, remember, f of x for us is the integrand. It's the thing on the inside of the integral. F of x is sine of pi x squared. Okay, so I'm going to get f of negative 0.6 gives me sine of pi times, pi times 0.36. You square 0.6, you get 0.36. So there's f of xi plus 1, and I divide by 2. So there's the area of the first trapezoid. Okay. Plus, then I want the area of the next trapezoid, 0.4 times. Well, I already know the height on the left here because I found it before as the height on the right for my first trapezoid, right? So this is just sine of pi times 0.36. And then the height on the right, well, what's that going to be? The height of this second rectangle, or sorry, of the second trapezoid. Perfect, exactly right. Plus sine of, I just plug in 0.4, or sorry, 0.2 minus 0.2 into sine of pi x squared. Well, when I square minus 0.2, I get positive 0.04, right? So I'm going to get sine of pi times 0.04 divided by 2. So in case it's unclear, we're just plugging in to get these heights. You're just plugging into f of x equals sine of pi x squared. Okay? That's where these heights are coming from. Okay? The next one, nothing changes. We still have plus 0.4 times. Again, we've already found the height of the left of this trapezoid because it was the height of the right of the last trapezoid. And that's going to be actually key when we're writing out the trapezoid rule in general. Okay, so we're going to get 0.4 times the sine of pi times 0.04 plus. Well, then the height on the right, I'm going to plug in x equals 0.2, positive 0.2. But because this function is symmetric about the y-axis, that's also going to be sine of pi times 0.04 divided by 2. And I know when you add something together and divide by 2, I could just write sine of pi times 0.04 there, but there's a more general form that we're going to be writing down here in a second. Okay. And we can continue the pattern. Let me shrink this and move it. We can continue this pattern. Plus 0.4 times sine of pi times 0.04 plus sine of pi times 0.36 divided by 2. And then plus the last one, 0.4 times sine of pi times 0.36 plus 0, technically, divided by 2. Okay. So there's a few special things we can do here that are going to show up in the general trapezoid rule. Okay, so let me add a page. Add page. What's the first thing? All these things have what in common? With the trapezoid rule, there's sort of two things that all these things have in common.
0.4.
0.4, very good. Anything else?
Dividing by 2.
Yeah, and with all of these, I'm taking, 0.4 times something plus something, divide by 2, right? So I'm out of all of these, I'm going to pull out 0.4 equals. I'm going to pull out 0.4 divided by 2. Okay? So when I do that, what I'm left with is, well, in that first term, I had 0 plus sine of pi times 0.36. There's from that very first term. right? I pulled out 0.4 over 2. Then in the next term, I have plus sine of pi times 0.36 plus sine of pi times 0.04. Then in the next term, I have plus sine of 0.04 plus pi times 0.04. Plus sine of pi times 0.04. That was that middle trapezoid, which was technically a rectangle, right? We have chats. The trapezoid, again, a trapezoid where one of the sides has a length of 0, we're still considering a trapezoid because the formula for the area still works. Okay. So then my next term, I have plus sine of pi times 0.04 plus sine of pi times 0.36. And then lastly, we have plus sine of pi times 0.36 plus a 0. I know that I wrote that out a little ugly, but when you look at this, the general pattern is my very first left side, that only shows up in one trapezoid, right? The very first height only shows up for that very left trapezoid, which in this case is a triangle, but that's fine. The formula still works. But for every other height, it shows up as both the right edge of a trapezoid and the left edge of the next trapezoid for every interior point. And then the last edge there only shows up for that rightmost trapezoid. Okay, so this shows up when we're writing this formula out. This shows up as, well, I still have 0.4 over 2 out here. I have 0 plus, then I have 1, 2 sine of pi times 0.36s to start. Plus 1, 2 sine of pi times 0.04s. Plus another 1, 2 sine of pi times 0.04s. Plus another 2. Plus another 2 sine of pi times 0.36s. So plus 2 sine of pi times 0.36. And then lastly, plus a single 0. Okay. So in this case, there's more simplification that can happen because the function is so symmetric. In general, the pattern for the trapezoid rule is going to be, notice this is my delta x over 2 times f of x0 plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3 plus 2 times f of x4 plus f of x5. Okay. This is for 5 trapezoids. This is the trapezoid rule for any function. It doesn't matter now that f is sine of pi times x squared. Given any function on the interval -1 to 1, this is what you would use as the trapezoid rule for 5 trapezoids. Okay. And in general, to use the trapezoid rule to approximate the integral from -1 to 1 of f of x with respect to x. By the way, why -1 to 1? Well, I'm not going to have time to get into it, but you can actually translate this to any integral by using a u substitution, which is pretty fun. Okay, but we're only going to focus on integrals from -1 to 1 for numerical integration. Okay, so to approximate this integral, the integral from -1 to 1 of f of x, using in trapezoids, we're going to let delta x, just like before, is going to be the length of the interval, which is 2, divided by the number of trapezoids. So 2 over n. You let xi be x0, which is -1, plus I times delta x. And you get the following. It's a little long to write out. So if I write this out without anything getting cut off, we would see that this is equal to 1 over n, 2 over 2n cancels, right? So 1 over n times f of x0 plus, and then all the interior points get 2's on them. So plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3, and on and on and on, plus 2 times f of x in -1. And then the first and last points, those only have a coefficient of 1. Okay, so plus f of x in. This is the trapezoid rule. For an integral on the interval -1 to 1.
Like you're making a trapezoid out of the...
Yeah, exactly. That's exactly right. Yeah, exactly. Yeah. Specifically, this is if we're being very technical, this is actually called the composite trapezoid rule. Composite. You don't need to know that it's composite. This is most people, when they refer to the trapezoid rule, they mean this. Okay. So let's look at the integral from -1 to 1 of the square root of 1 minus x squared with respect to x, which we know, by the way, this is the area of half of a circle of radius 1. So this is pi over, we know that the exact value of this is pi over 2, right? So we can actually use the trapezoid rule to get an approximation of pi over 2 if you are into that kind of thing. I am. I don't know what you guys are into. I don't judge. Okay, but let's use the trapezoid rule. So again, delta x, just like before, delta x is 1 minus -1, 2, divided by the number of trapezoids. For us, that's 5. Okay, which again is 0.4. So there's delta x. xi is going to be -1 plus I times delta x, or in other words, -1 plus 0.4 times I. Okay, so we could go through the trouble of drawing this out, or we could just plug into the trapezoid rule that we know now. Okay, so we know that this is going to give us the integral from -1 to 1 of the square root of 1 minus x squared. This is f of x for us. F of x is the square root of 1 minus x squared. So the square root of 1 minus x squared. I think I misspoke a second ago. I'm sorry. Okay. But this is going to approximately be equal to, well, what's the formula say? 1 over n, or 2 over 2n, however you want to think of it. 1 over n, so 1 over 5 times, well, let's just write it out for a second. F of x0, well, x0 is -1, plus 2 times f of x1, well, f of x1, that's going to be -1 plus 0.4. So that's -0.6. plus 2 times f of, well, again, you take another step of 0.4. I get 2 times f of minus 0.2. Then plus 2 times f of 0.2 plus, oh, come on, plus 2 times f of 0.6, and then plus f of 1. Okay. You're going to get really into writing down the 2's. You need to remember to not write a 2 on the last function evaluation. Okay, so this is equal to 1 over 5 times. What is f of negative 1? Zero, very good. 1 minus negative 1 squared is 0, and I take the square root of that, I get 0. Plus 2 times 0.6 squared is 0.36. So when I take 1 minus that, I'm going to get 0.64, the square root of 0.64. But what's the square root of 0.64? Well, I'll just write it out for now.
0.8.
Yeah, it's 0.8, right? The square root of 1 minus 0.36 is the square root of 0.64, which is 0.8. Plus 2 times f of 0.2. Well, this one doesn't simplify quite as nice. I'm going to get square root of 1 minus 0.04. So that's the square root of 0.96. And again, I'm just, for all these, we're plugging into here, okay? If you need a little more time to do that, that's totally fine. Then the next one, I'm going to get 2 times, well, f of 0.2 is the same as f of negative 0.2. So I'm going to get 2 times the square root of 0.96 again. F of 0.6 is the same as f of negative 0.6. So I'm going to get plus another 2 times 0.8. And f of 1 is 0 again, right? Any questions on this so far? Okay, so we're not going to get into the Simpsons rule, but if we actually calculate this out really quick, I'm going to get 1 over 5 times. For those at home, I'm just using the calculator on my MacBook. So 2 times, really 4 times 0.8 plus 4 times 0.96 gives me 1.42. We'll say 1.424 about. This is about 1.424. Okay. What about pi over 2? What's that equal to? About 1.571. So, is our approximation great? No. Is it closer than just guessing? Yeah, probably. So, that is the trapezoidal rule, or the trapezoid rule. Simpson's rule, I was going to use Simpson's rule next to approximate this. That's where we'll pick up on Thursday before we start reviewing for the final. But Simpson's rule, instead of using trapezoids, is going to use parabolas. Okay, so, and Simpson's rule, it has a very similar formula, only instead of 1, 2, 2, 2, 2, 2, 2, 2, 1 for all those coefficients, we get 1, 4, 2, 4, 2, 4, 2, 4, 1, and so on. Okay, so it's going to be, once we work it out, it's something that we'll be able to again, just plug into instead of drawing the parabolas every time. But the Simpson's rule is going to be even more accurate because we're using something that should more closely approximate the shape that we're looking at. Okay. So, do we have any questions before we head out? Okay, because I didn't get to Simpson's rule, I'm going to say quiz is postponed, quiz postponed until Thursday, okay? On Thursday, I'll post a quiz with these integration rules, and you guys will be able to take that quiz on Thursday, okay? So thank you everybody for being here. If you do think of any questions, I'll have my email open all day, and I'm in office hours Wednesday and Friday, okay? So see everybody on Thursday.
Thank you.
Thank you.